The invisible giants, understanding black holes. For millennia, humans have mapped the glowing stars, planets, and galaxies. But what about the dark spots? What about the things we can't see? Today, we are talking about the universe's ultimate vacuum cleaners, black holes. So what exactly is a black hole? Well, it's not actually a hole at all. A black hole is a region of space where gravity pulls so intensely that nothing, not even light, can escape. Because no light can get out, people can't see black holes. They are entirely invisible. To understand how they get this strong, we have to look at how they are born. Most black holes are the ghosts of massive stars. When a giant star reaches the end of its life, it runs out of the nuclear fuel that keeps it burning. Without that outward energy to push against the star's own massive weight, gravity wins. The star collapses in on itself in a massive explosion called a supernova. What's left behind is an incredible amount of mass packed into an impossibly small area. Imagine taking an object the size of the sun and crushing it down to the size of a single city. That mind-boggling density creates a gravitational pull that bends the very fabric of space and time. Every black hole has two main parts you need to know about. First is the event horizon. Think of this as the point of no return. Once anything, a comet, a planet, or a beam of light, crosses the event horizon, it is trapped forever. It requires a speed faster than light to escape, and since nothing is faster than light, nothing gets out. Second is the singularity. This is the very center of the black hole. It's a single point in space where all the matter of the black hole is crushed into infinite density. The laws of physics, as we know them, completely break down here. Now you might be wondering, what would happen if you fell into one? Well, astrophysicists have a highly scientific term for this: spaghettification. Because the gravity is so extreme, the pull on your feet would be vastly stronger than the pull on your head. You would be stretched out vertically and squeezed horizontally until you resembled a long, thin noodle of pasta. Not exactly an ideal vacation spot. Despite their destructive reputation, black holes don't just wander the universe eating everything. They follow the same laws of gravity as everything else. If we replaced our sun with a black hole of the exact same mass, Earth wouldn't be sucked in. We'd just keep orbiting a dark center, though it would get extremely cold. It is completely understandable why this concept trips people up. Pop culture and science fiction have trained us to think of black holes as cosmic vacuum cleaners that violently suck up everything in their path. To understand why a black hole wouldn't suck up the Earth if it replaced the sun, we have to gently untangle the vacuum cleaner myth and look at how gravity actually works. Here is the breakdown of the physics behind that statement. 1. Gravity depends on mass, not size. The gravitational pull between two objects is determined by only two things: the mass of the objects, how much stuff they are made of, the distance between them. Isaac Newton's law of universal gravitation represents this mathematically as the force of gravity, F, relies purely on the masses, m1, m2, and the distance squared. Notice that the physical size or volume of the object is not in the equation. 2. The mass hasn't changed. Our sun weighs exactly one solar mass. If a wizard waved a magic wand and crushed the sun down into a black hole, it would shrink from being 864,000 miles wide to a sphere only about 4 miles wide. However, it would still weigh exactly one solar mass because the black hole has the exact same mass as the sun, and the Earth is still the exact same distance away, 93 million miles. The gravitational pull on Earth remains completely unchanged. Earth's forward momentum would remain perfectly balanced with the inward pull of the black hole, keeping us in our exact same orbit. 3. Black holes don't suck. A vacuum cleaner works by creating a difference in air pressure, which pulls dirt in. Gravity doesn't work like that. Black holes only pull things based on their mass. They do not have any extra sucking power just because they are black holes. If a stray asteroid flies near a black hole, it is just as likely to slingshot around it and fly away as it would if it flew past a normal star of the same weight. Why are black holes dangerous then? If they don't suck, why is their gravity considered so extreme? It all comes down to density. Because a normal star is huge, you can only get so close to its center of mass before you literally bump into the surface of the star. But because a black hole is crushed down into a tiny point, you can get much, much closer to its center of mass. As you get closer, the force of gravity gets exponentially stronger. The danger of a black hole isn't that it reaches out and grabs you from across the galaxy. The danger is that if you happen to wander too close, its incredibly small size allows you to cross the point of no return, the event horizon. But safely out at 93 million miles away, Earth is perfectly fine. We would just be orbiting a tiny, invisible, 4-mile-wide sphere in the pitch black, and the entire planet would rapidly freeze without the sun's light and heat. Black holes are extreme, bizarre, and terrifyingly beautiful. They test the very limits of human knowledge and remind us just how wild our universe really is.